Hello and welcome to this Tau language progress update. The Tau language, the first logical language that can speak about its own sentences utilizing the theory of Boolean algebra, is designed as a software specification language. Its unique ability to be executed to yield correct by construction software is said to make a profound impact in the world of expressive software specification languages. In this progress update, we present various Tau language and REPL features which are already implemented. The Tau REPL is our interface to the Tau language with the end goal to demonstrate the execution of Tau programs. I'll introduce part of the basic syntax of the Tau language, as well as commands and features of the Tau REPL. Furthermore, I'll show how to define functions and recurrence relations and how to use the normalizer to normalize Boolean functions and Tau formulas. We will see some examples in this video, and more in-depth demonstrations of features of the Tau language will follow in later updates. So let's get started. The Tau REPL keeps track of all the results that you inputted in a history. There you can also store Tau formulas and Boolean functions. The history works like an array, so the first stored formula or the first result is stored at position 1, and to access the elements of the history, you can use a relative or absolute notation. The relative notation is percentage minus, and then you input the position. The intuition is that from the end of the array, you go back the number of steps that you inputted in position, but we simply type percent in order to just access the last result. Whereas the absolute notation is percentage position, and position just denotes the place in the array where the formula is stored from the start. We can store several functions in the history by simply typing them. As usual, pipe stands for disjunction and and stands for conjunction. As you can see, conjunction can also be omitted so that we just write xy instead of x and y. The apostrophe stands for complementation. 1 and 0 respectively stand for the corresponding constants in the Boolean algebra, where 1 denotes the top element and 0 denotes the bottom element. To recover from the history, we can use the following commands. Hist%, here we see the percentage symbol again, and also here it denotes the last position. History percent minus 1 denotes the previous position. So we are going backwards one step from the end. And history percent 1, this is the absolute notation, and it denotes the first formula we ever stored in our history. Also, we can output the whole content of the history. Just type hist, and it prints all stored formulas. As previously commented, apart from Boolean functions, we can also store Tau formulas with free variables. For example, x equals 0 and y equals 0 or z equals 0. Note that when talking about Tau formulas, we are not using the same connectives as when talking about Boolean functions to distinguish the Boolean function layer from the logical layer of the Tau formulas. Here, the double pipe and the double and stand for disjunction and conjunction. In contrast, the caret stands for the exclusive OR, and the exclamation mark stands for negation. Greater minus equals naturally stands for equivalence, and minus greater stands for implication, as is usual in logical notation. X equals 0, question mark, y equals 0, column z equals 0, is the if-then-else or conditional operator known from programming languages such as C++, which we can also use within Tau formulas. In addition, we can use quantifiers. All x exists y, x equals 0, and y equals 0, showcases universal and existential quantification in a simple statement. We can also include constants from the Lindenbaum-Tarski algebra of propositional logic represented by BDDs, meaning that the Boolean function we input is internally stored as a VDD and treated as a propositional formula. The type column inside curly brackets syntax denotes constants in the supported types, which we previously called our base Boolean algebras. In the above example, we declared a constant in the BDD Boolean algebra corresponding to the simple Boolean function x. We can include temporal variables in formulas. Variables starting with I denote input variables, and variables starting with O denote output variables. For example, O1t equal I1t or O2t unequal I2t denotes a tau program that says that the output 1 at time t equals the input 1 at time t, or the output 2 at time t is unequal to the input 2 at time t. The execution procedure for such a formula will later generate a sequence. In this example, as before, the double pipe stands for disjunction, and the double N stands for conjunction, whereas the exclamation mark still stands for negation. Also, we can include formulas with global operators, which will deal with the Boolean algebra of models for tau formulas. In this logical layer, the triple N stands for global conjunction, and the triple pipe stands for global disjunction. We can have global negation as well, and the symbol to denote this is the minus. We can also have formulas that involve constants over the tau Boolean algebra itself, as the tau language is the first language that speaks about its own sentences. In the above example, as we have a constant in the tau Boolean algebra, the type could be omitted. This allows us to write tau specifications that can talk about tau specifications themselves. Also note that we can use this definition recursively to define tau specifications that talk about tau specifications that talk about tau specifications, and so on. In the near future, we are changing the syntax for our constants in order to have a more clean notation. It should be noted that we can have formulas that involve all the above-mentioned elements at the same time. So what we presented here are really just basic examples. The above notations used to access the history can also be used in the commands. For example, the following commands will compute the DNF of a Boolean function parsed as an argument or as a memory position. The first example shows how to store a Boolean function, then we store another Boolean function, and then we convert the formula stored at the relative position 1 to DNF. We can also convert the first formula ever stored in the history to DNF. But of course, we can also provide the Boolean function directly to the DNF argument. The same happens when using formulas. The following command will convert formulas to CNF. Again, we store a formula, and then we convert this formula to CNF. Next, we access the formula by the relative position 1, and then we access it by the absolute position 1. Since there's just one formula in the history, the relative and the absolute notation coincide. As was the case for the DNF command, you can also directly provide a Boolean function to the CNF command. Apart from inputting Boolean functions and tau formulas directly, you can also bind them to function names. The same is true for recurrence relations. As with the history, such definitions are stored in an array-like structure. You can check them in a notationally similar way. Just the keyword changes from hist to depth. The percentage still denotes the last position stored. The percentage -1 still denotes the relative position, so counting from the end, and the absolute position %1 still denotes the first function or recurrence relation ever stored. To print all definitions you entered, just type defs. In order to use the definitions you defined, you just invoke them by their name. For example, h of y defined as 1 defines a Boolean function with the name h. Now you can normalize a function involving this defined Boolean function by just calling h. In the future, we will improve the syntax. Namely, instead of using column equal, column equal, and column equal, we will only be using column equal. The $sign will disappear as well, and we will consider only variable names in Boolean function and recurrence relations definitions. Let us demonstrate several commands related to normalization and its inner workings. The qlm command eliminates the most inner quantifier from a formula. For example, qlm all x equal to 0 eliminates the for all quantifier. As before, you can also pass a formula stored in the history to the qlm and the normalization command. Finally, the following example illustrates the use of the new Boolean function normalizer and the new quantifier elimination algorithm. It uses the normalize command to prove the validity of a formula in the first-order theory of atomless Boolean algebra. This is because we assume non-type variables to be of this kind by default. In fact, our procedure can decide the validity for any formula in the first-order theory of atomless Boolean algebra. The following example says that for all x there exists a y, such that for all v there exists a w, such that the complement of x and y is equal to 0, and v plus w is also equal to 0. The new Boolean function normalization procedure uses the Boole decomposition and can thus minimize redundant parts of a formula. In the example, xyz vw or xyzv or xyz or xy or x, we see that it reduces just to x. This is because all other disjuncts are an implication of x. The Boolean function normalizer also gives canonical output, meaning that two equivalent but syntactically different Boolean functions will be normalized to the same syntactical expression. The following is a simple example of this. This concludes the first Tau language demonstration. Thank you for watching, and if you find anything unclear, please feel free to reach out to us. We are looking forward to provide you with new demonstrations in the near future. Thank you and have a good day.